And I'm just going to leave, close the door and leave you to it.
Okay, is it recording now?
It's recording now, but I'll cut it. So I
Okay.
can put cut in.
Okay, thank you. Okay, so here we are. This is part B of question 1. We've hopefully found this differential equation with a bit of mucking about and swapping of variables. Now, it's important to say again, if you are struggling and only halfway through part 1 and you kind of give up, don't worry. Part 2 of these questions, if they've given you the differential equation, you can hack on with this bit if you find this bit okay. So this is a differential equation. It's got dH dt in it, and it's also got an h in it. And they've given us some information. They've given us a point for t and h, and they've also said, well, what's t doing when h is 0.5? So we need to turn this into a relationship between t and h, which is basically going to be solving it. We don't want this dH dt anymore. This is the gradient of the line, or the rate of change. So we need to solve that and get an expression with h and t. So the way we do that is we're going to end up splitting the dH and the dt and put them on different sides. This dt is going to travel over to this side because it's the bottom part of the fraction. So again, we're thinking of our dH dt as a fraction. So I'd end up with something like this. So always when we're multiplying these, that works. So when we multiply by dt, we end up with this. Of course, this prevents some problems because we would also put in the integral signs at this point. And this is fine, but this part on the right hand side, we can't differentiate this integrate this h with respect to t. So we need to get all the h's onto this side before we can do anything. So before we get to that point, let's put our dt back over here. And this time I'm going to divide by 4 minus 5h. And what that does for us is it gives us this equals 1. So the h is now on the correct side. Notice we can't just add the 5h and leave the 4 behind because then we won't have it multiplying the dh. So it's quite important that we divide or multiply when we're rearranging here. So what this gives us is that now I've got 75 over 4 minus 5h on this side. dh, that's okay, that's the right variable, and we've got that 1 left on that side. So these are two integrals that I can do, so this is differential equations. If you need to look that up, that's what we're doing. Okay, so we've split the h dt, we've got our integrals there. I'm going to treat this as an indefinite integral. But what you could do, if you're happy to do so you can put in your values of h and do this as definite integrals. So don't worry, I don't usually do it this way, but you could take h from the first point, 0.2, up to 0.5, and you'd have corresponding values here, maybe t equals big T, to my invented value. You could do it this way. This side would just be t, and on this side you'd get something more interesting. So that might be a quicker way to do it. If you want to, you can go ahead and do that. Either way, we've got to integrate. So you might notice this left hand side, this 75 over 4 minus 5h, is of the form 1 over something. So remember, this is ln x plus c, or the ln x sort of form. So we're going to get 75, it's just a constant at the front. Then we've got ln remember to use modular signs, just so that we can't take the ln of a negative number, so that sits in there on that side. And there's something that's a little bit tricky here, which is that we've got a minus 5h, not just an h. So if we were to differentiate this to go back to the integral, if we were going from here to here, chain rule dictates what? I'd have to multiply it. To get from here to here, I'd have to multiply it by minus 5. Just because that's the differential of the inner function. So chain rule pops up in very small ways like that. So that's okay, we can just adjust the constant at the front. So we need to divide by minus 5. So I'm going to put a minus a fifth on the front there, just to compensate for that. So when we work backwards, this minus 5 will cancel out with that. Okay, so just chain rule happening with a sort of linear function. On this side, or the integral of 1, we'd have to put a t next to it, so we get t there, and we're going to put our constant on that side. Remember, we don't need constants on both sides. This c can absorb whatever the constant was on this side. We just need to make one adjustment. Okay, so that's our integral, and this, I think, a fifth of 75 is 15. So that may be a little bit neater. And we need to work out this c. Now, of course, this is where this data comes in that they've given us, this fixed point, that when t is 0, h is 0.2, which we could have done as a definite integral. We can put that in here and find c, sort of doing the same thing but by a different route. So if I put 0.2 in, again, little handy hints if you are substituting, it's worth actually substituting and putting it in brackets just so you don't make a slip up. 5 times 0.2 is just 1, so this ends up as c equals minus 15 ln 3, so this is just 4 minus 1 in the bracket. Okay, so c is minus 15 ln 3, so I can put that back into my main equation. We've got minus 15 ln 4 minus 5h is equal to t, which is the variable, minus 15 ln 3. And the actual question says, what is t at h equals 0.5? So let's put 0.5 in there instead. And we get minus 15 ln 4 minus 5 times 0.5 equals t minus this c, which is not changing, and then we can work out t from there. So you will need log rules at this point. We haven't really used the log rules so far, apart from knowing that the integral of 1 over a linear, a single power of a variable, gives us ln. But here we've got to rearrange to get t. If I add this constant on both sides, I get 15 ln 3, that's the c, minus 15 ln, and here I've got 4 minus, well, 5 times a half is 2.5, so I've got 4 minus 2.5 is 1.5. Great, that's a positive number. That 15 can come out of the front. We've got ln 3 minus ln 1.5. And this is where we need our log rule, is that when we've got one ln minus the other, see if you can recall what happens, we need to, if we want to make that into 1 ln and simplify, we divide the first one by the second one. So this is 15 ln 3 over 1.5, and 3 divided by 1.5 is just 2, so we get a final answer. Let's write it so you can, so it stands out a little bit, of t equals 15 Ln 2. So that's our final answer, is that t is 15 Ln 2. There's quite a lot of marks for that, 6 marks, because it is quite a lot of work. It's tempting at this stage, you know, if you do get lost in your log rules, it might be tempting to put it into the calculator. If your calculator keeps it as Lns, brilliant. If it ends up with giving you answers that are decimals, a decimal answer is okay. This is the perfect answer. You have a look on that mark scheme to see if they give you the marks for a purely decimal answer, but at this stage here, where we just got t equals, you could put it in your calculator if you forget, and you'll get, you should get most, if not all, of the marks. But there may be a mark for showing off your log rules, of course. Alright, I hope that made sense. I'll have a go at the last question on the sheet, because I think that's got an extra trick. But there's quite a lot in these rates of change questions to work on. But there will be one in the assessment. Okay, take care.